Hey, right, we're on. Okay, so this is a summary of. Damn, I don't suppose I'm allowed to ask questions because we're late this time, aren't I? Summary of the material that Mike lectured you on. It really shouldn't be any sort of a surprise to you because you've obviously been revising this very hard. He's also listed the books that cover the material that he's covered. Okay, but this perhaps is a little bit more central. This is the stuff that he wants you to know. You don't need to know integration and differentiation. Not this year, the next year you do. Define, okay, so rate constant, activation energy. These names should be familiar to you. You need to be able to define and write down what they mean. Steady state approximation. Graph stuff, he says usually first order, but not always. So you need to know how to derive zero order and second order rate constants as well. You did that in the practical, you should be familiar with that. Arrhenius plots, effect of temperature on rate constants, you should be familiar with that as well. Calculational, I'm not sure that's a word. So once you've got a graph, you need to be able to derive the activation energy, the pre-exponential factor, the rate constant, and of course say what the reaction order is if you don't know. There we are. Derive E, the activation energy, from two values of the rate constant. So you might have this at different temperatures, or you might have different rate constants at the same temperature with different concentrations. You need to be able to work out activation energies. And finally, the pre-exponential factor. All these slides are. This is all on Learning Central as well. So you can pick that up from there. Okay, all the material that you need is in the handouts, the lectures, tutorials, and past papers. And I would say the past papers has got to be your most important resource. Those are available on this website. It's the Cardiff Library. Last year's spring paper, for some reason, isn't there, but David has put it up on Learning Central. So if you go into the module, you'll see the paper in front of you. Okay, so that's just material that Mike's covered. And the equations, the kinetic equations. These are the ones that Mike wants you to remember. I'm not sure the formatting quite worked. I was looking at this just before I came in. But they shouldn't be a surprise to you anyway. You know what the rate equations should be. So these are the rate equations. First order, second order. I had zero order in there, although Mike hasn't got that. You did meet that in the practicals. Zero orders, just a straight line. Arrhenius equation, the equilibrium, where you've got the rate constants forward and back. The ratio of those will give you the equilibrium constant. Pre-equilibrium, Michaelis-Menten kinetics, the ideal gas laws, Van der Waals, where the ideal gas laws break down, and you have to start thinking about Van der Waals interactions and non-ideality. Collision theory, you need to know the equation. Molecular speeds, you need to know that equation. And he's listed some of these as required for calculations and graphs, and others just for general description. So the Michaelis-Menten, for example, he's not expecting you, it seems, to do calculations of that. He just wants you to explain what it's about. Okay, right. First set of examples. So this is from the 3101 last year's resit paper. That is available, and I'll just turn some lights on, and we can have a look at some of these questions. Okay, so first question. Take 60 seconds for the concentration of a reactant to decrease to 1/6 of its earlier concentration. Calculate the rate constant, assume it's first order. So what you need to do is pick out the key phrases, the key bits of information. So the first thing is, it's first order. So you know then that the log of A is equal to minus KT plus the log of the initial concentration. It takes 60 seconds for the concentration to go down to 1/6. So you know that A over A0 is equal to 1/6, where T is equal to 60 seconds. And we've got to find the rate constant. So if we look at this equation now, we know all the information we need to find the rate constant. Let's rearrange this a little. So that's going to, we can rewrite that as log of A over A0. I know I'm going through this quickly. If anybody needs explaining how I got to that, I'll go over it afterwards. That's going to equal to minus KT. A over A0 is going to be 1/6. So we've got log of 1/6. That's going to equal to minus K times the time is 60. So our rate constant K is going to be equal to log 1/6 over 60, and the units are going to be seconds to the minus 1. If you do that calculation, it comes out to be, or at least this is what I got it to be, I hope it's right, 298 seconds to the minus 1. Okay? But the key points are spotting first order, and as soon as you see first order, think what equation do you know for first order. The integrated rate equation for first order is usually the one you're going to need. You might need the half-life for first order. I think we've got an example of that coming up. Okay, next question on kinetics on this paper was question 6. That's both